Hi everyone, my name is Art and I'm here to give a deep learning tutorial as well as go over some applications. If you have any questions, feel free to reach me at artitw@gmail.com. That's artitw@gmail.com. So first let's go over some of the uses or applications of deep learning that are really groundbreaking and impressive. Siri or other voice recognition systems by Android, say, are a good example of applying deep learning to voice recognition and understanding and transcription. Another application is with image processing, whereby you can take a photo, as in section A shown here is a normal photograph, and you can combine it with well-known paintings, for instance, Starry Night in section C, and you combine a photo and Starry Night, and it sort of hybridizes the two and gives you a Starry Night theme of that photo, and you can do so on and so forth with other types of paintings to that photo. This is an example of deep learning. A very recent progress with deep learning is using it to play games like Go that were previously unsurmountable by computers because there was just too many possibilities on the Go board. Go in Chinese is Wei Qi, by the way. Korean is Paduk. And it was demonstrated recently by Google DeepMind that deep learning algorithms can beat and defeat the top Go players in the world. So this is extremely significant result because we're going to see that deep learning is essentially the path that is closest or is the most promising path towards AI, artificial intelligence, that humanity has achieved so far. Now, what is the actual basis or the fundamentals or the background behind deep learning? It has to do with the brain, and not just the human brain, but brains in general of animals, etc. It's been demonstrated that a section of the brain, as shown in this example here, which is the red shaded portion, sections 41 and 42, the auditory cortex of the human brain. So this auditory cortex has been trained for listening. We use this part of the brain for listening and processing that. And it's been shown that if you rewire the vision part to this auditory cortex, that we can learn to see using that auditory cortex. So what that sort of suggests, and this has been repeated on animals of all sorts in terms of rewiring the brain and making different parts of the brain learn new things and learn different things, is that there is a fundamental learning algorithm inside the brain. And this fundamental learning algorithm can adapt itself over time, with training data, that is, and experience, that over time it can adapt itself and learn to do different tasks and perform different tasks and get good at those things, such as vision and hearing. And other examples, like the bottom images here, is like if you have some sort of a vision camera that hooks up to electrical sensors, and then you stick that onto your tongue, eventually your tongue can learn to see as well. So that's another direct example of or direct evidence supporting the existence of a fundamental learning algorithm in the brain. So let's take a closer look at what's inside the brain. And that's what deep learning really is. Deep learning is trying to, an artificial intelligence, is trying to emulate, trying to simulate the brain. And so inside the brain there are neurons. This is an example of a neuron here, and this neurons have dendrites, which are the branching-like things, and the dendrites are input wires into each neuron. And in each neuron there's a nucleus and the cell body, and then that's where the learning algorithm is. And then there's the axon, which is the outputs that come out. So how does a computer emulate this structure inside the brain? And of course the human brain has billions of these. And the step is what can the computer do to emulate this? So one of the most common examples of deep learning is learning how to read handwriting, human handwriting. In particular, there's this handwritten digits, handwritten numbers. We can easily read it and recognize it as 504192. But if you write a conventional computer program to try to pick out these numbers, it turns out to be a challenge, and you get really low accuracy. But with deep learning, you can get very good accuracy, and in fact, you can get better than humans too. So what is what is the approach taken to recognize these handwritten digits? Well, it's a computer after all, and a computer processes data. So what you have to do is you have to break down these images into its data components. In this case, since they're images, they can be considered 2D pixel intensity input data or a 2D array of data. For the common handwritten digits, we can break it down into 28 by 28 pixels, which is a 784 inputs into the neural network that we're going to build using the artificial neural network, so to say, because they're not real neurons in the brain, but they're simulated by the computers. So in each of these simulated or artificial neurons, what we have is something very similar to what we saw earlier with the dendritic inputs and then the axon output. In this example, there's x1, x2, x3, which are inputs. There are 3 inputs. There could be more or less. It's really up to the design of the engineer. And then there's an output. And so the question is, what is inside that circle? What is that learning algorithm inside that circle? And people have played around with different learning algorithms. Shown here is one learning algorithm. I'm going to call it learning algorithm number 1. And this is the most basic learning algorithm for artificial neurons. And it goes like this. The output is either 0 or 1. It's 0 if the sum of all the weights times the inputs. So W is the weights and X are the inputs. And if you sum up each one, if it's less than the threshold, it's 0. If it's greater than the threshold, it's 1. So the inputs are determined by whatever data you have. However, the weights and the threshold, we need to choose those, at least in the beginning. We have to initialize them with some sort of value. And we use the data to train it, and this is where the learning comes in. You adjust the weights and the threshold to learn. And for those who are more mathematically inclined, you can retranslate this learning algorithm into more matrix-friendly operations. For instance, W vector dot the X vector plus the B vector. B in this case is negative threshold. But it's the same idea. And you can see that this is actually a step function. It's 0 and then it just rises abruptly to 1 when it crosses that threshold, or negative B. Now, remember, our brains have billions of these neurons wired together, and that's how we can learn. And one neuron's not going to do anything too significantly, so we're going to build a network of neurons, and hence the neural network. And since it's emulated by the computer, we're calling it an artificial neural network. And this artificial neural network consists of inputs. The first 3 points there is just examples of inputs that go into the layer of which consists of 4 artificial neurons, the middle layer. And then those 4 artificial neurons go into the output neuron. So there are 5 artificial neurons in this network and 3 input nodes. Okay, so how does it learn? Again, remember, we're trying to figure out what the W's, the weights, and the biases, B's, are. In this case, let's just focus on the W's for now, but it's the same idea with the biases. Basically, you feed in the data that you have pre-labeled, or you have to feed in pre-labeled data, or data that you know what the output should be, at least to train it in the beginning. And then you compare the output from your neural network to the output that you know is correct, the ground truth, the labeled ground truth. And then if it's not the right output, then you have to adjust your weight somehow. You have to have a feedback cycle. You have to iterate through this feedback cycle to converge such that the error, you're satisfied with the error is minimized. So as you can see, you're going to have to define a loss function or error function at some point to be able to quantify how good or how accurate you're getting to whatever output you need. But it's an iterative process, and it occurs in a feedback loop. You have to keep training. And this is very much like human experience. If you learn how to drive a car, you learn how to walk, you learn how to ride a bike. You don't get it exactly right the first time, but you adjust yourself and you learn. Okay, so I mentioned that learning algorithm number 1 is the most basic one. It turns out that doesn't work well. A learning algorithm that works better is shown here, which is learning algorithm number 2. This learning algorithm number 2, I'm going to call a sigmoid function. Well, I'm not going to call it, but that's what it's considered, a sigmoid function or a logistic function, if you're familiar with that. I'm not going to go through the math in much detail because if you're interested, you can just search it up and learn it yourself. But basically, the sigmoid function is sort of like a smoothened step function from before that goes from 0 to 1. So it's you don't have abrupt changes. Let's say you're trying to learn, and just because the input varied slightly, your output varied significantly because you're right at that abrupt change, that slope. You don't want that in the learning process, hence you want something smoother, and that's where the logistic function or sigmoid function comes in. And using this, the learning and training the neural network improves significantly. And there are other learning algorithms that people try that work or that potentially works even better, obviously, depending on the application. There's a hyperbolic tangent function, there's the rectified linear unit function, and others. It's been researched very well. Now, as a friendly reminder, in recognizing this handwritten digits, we need to have 784 input neurons because there are 784 pixels. Remember, it's 28 by 28 image for each one. And then for the hidden layer, the layer that's in the middle, the second layer with the main artificial neurons, how do you choose? In this case, shown here is 15 neurons. But it's really, you have to figure out how many neurons are good, and you can imagine iterating, say, through a for loop or something to figure out what's the optimal number of neurons. But shown here is 15, and that's really up to the deep learning engineer or scientist to figure out. And there's the output layer, which classifies it as either 0, 1, 2, 3, etc., to 9. So this is a multinary classification problem. So you can imagine that this neural network, each part of it is learning something about each digit. For instance, let's take this 0, for instance. The part of the neural network might say, is there an edge on the top left that looks like that part? Is there a curve on the top right? Is there another curve on the other way on the top and the bottom left, and another curve on the bottom right? And then combining the existence of these values together, it can weigh out probabilistically whether it's a 0 or not, and quantify that. So far what I've talked about is actually it hasn't been deep learning yet. It's just neural networks, artificial neural networks, and this has existed for like 50 to 60 years or something. And it works, but it doesn't work. It doesn't work magnificently well. So there was a hiatus or sort of a winter for artificial intelligence and for some time because people couldn't figure out how to make it work better. But in the past 4 to 5 or even 6 years, there has been advances to these artificial neural networks, and that's where deep learning comes in. All right, so let's talk about that. How do we get more deep? Because right now I'm considering it a shallow network. Well, the way we get more deep is that, so first of all, for recognizing handwritten digits, that normal neural network actually works very well. But what if you want to do something more complicated, like recognizing what's in this photo? Is it a human in this photo, or what is it in this photo? That gets tougher. You can't really, if you use a normal neural network, it won't work well for this. So we need to use deep learning to make this very effective. And how does deep learning approach this problem? Well, we approach it by taking a hierarchical breakdown of the features in the photo. If you have the input pixels coming in, we need something to identify. Is there an eye on the top left of the photo? Is there an eye on the top right? Is there a nose in the middle? Is there a mouth below? Is there hair on top? And you combine this information together, and then you judge from that. Again, you quantify the probabilities, and you say, what's the probability it's a human? It's very high probability, very low probability, etc. Kind of like the example with the 0 digit earlier, where you break down the different edges on different quadrants and stuff. But in this case, you're trying to actually look for different features of what defines a human, and that's what humans naturally do when we look at things. Does it have an eye? Does it have a nose? How many legs or how many wheels does it have? Is it a bicycle or is it a car? Anyway, so we can break that down even more. For the eye that's in the top left, how do we judge if it's an eye? Well, does it have an eyebrow? Does it have an eyelash? Does it have an iris? And you can imagine we can go many, many layers, and that's where it gets deep, because we're really starting high level and we're breaking it down. We're going deeper, all the way down to the raw pixels. Is it what we think it is? Or, yeah, that's right. And it's been demonstrated that this works. This is some results from Andrew Ng's group, whereby they've broken down the features of the human face in different layers. Let's start from the right. The first layer is the full face of different types of people, or male and female. And then the next layer, you're looking at the eyes, you're looking at the nose bridge, you're looking at the chin, the nose, the mouth, etc., etc. And then you go down even deeper, one layer, and then you have these edges that don't represent, we don't, as humans, we don't recognize it anymore, because the computers are using these edges as features to make up the next layer. So the left layers make up the next layer on the right, and it builds up so forth, such that you can form a face. And that's how the deep learning algorithm recognizes if it's a face or not. So in order to perform this, like I said, one layer of the neural network like we had before is not going to fly. So we need a deep neural network, whereby each layer breaks it down as what I was talking about earlier, where the final layers, where it's the highest level, where it has the face. The layers to the left are more lower level and such. But it turns out if you just have a deep neural network that's shown here, it still doesn't work well. And so the real advances so this is a deep neural network. I personally wouldn't consider it deep learning yet. The real advances come in when we add features called, or we add operations to our algorithm called convolution. So what convolution does is convolution scans portions of the image, like maybe a subset of that image, a small little frame. In this case, we're taking a 5x5 feature. It's called feature mapping. We're taking a 5x5 map, and we're going to scan this map across the entire image to form with the weights and biases in this case, and to form the next layer. So in this case, the input neurons form the first hidden layer in 2 dimensions. So earlier, the normal neural networks, those were called flattened or multi-layer perceptrons, and those are more one-dimensional neural networks. In this case, this is a 2-dimensional, because we're really considering the 2-dimensional spatial variation here. And that's key, because the image is, after all, 2-dimensional. So this process is called convolution. And as you can imagine, this helps with translational invariance, because if you have a face, that face of a human doesn't necessarily have to be in the middle. It can be shifted to the right, shifted up, staring down, and so on and so forth, but it's still a human. And if us humans, we can recognize that, we should get deep learning to recognize that as well, and that's where convolution comes in. It's not obvious yet, but that's also where this other operation called pooling comes in. And pooling is really an aggregate and reduce operation. What pooling does, and the most popular one's called is max pooling, is that you examine again a map, a subset of that, a sub-image, and you look at the pixel intensities, and you say, what's the maximum pixel intensity? In the top left, the red, the maximum is 6. So then you take that value, 6, and you form the new 2D output layer. And then and you can go on and so forth. The next, if you take another stride of 2 pixels to the right, then you look at 2, 4, 7, 8. The biggest one is 8. So then you take 8 and you move that onto the next layer. And using the deep neural network that is in the 2D formation of the image, you add convolution to that, and you add pooling to that. That's really what deep learning is. And of course, there are other deep learning techniques and algorithms, but this is one of the popular ones that work well for image processing. And so shown here is a picture of a boat that's docked at the shore, and we're going to perform convolution on it. In this case, there are 3 convolution maps, so we're looking at 3 features. For whatever reason, the authors of this paper chose 3 features, and they're convolving it. And then from those 3 features, you do a max pooling, also you do a max pooling across that, so then again, you have 3 sets of data for the max pooling. And from that max pooling, you do a convolution, and this convolution has looks like 2 features each. So 2 on the 3, you get 6, and that's where that 6 images come in. And then you pool again, and then you flatten that to the 1D neural network, and you have 2 of those fully connected layers, and then you have the output prediction. And then the output prediction, this paper shows that we're only trying to classify 4 different things, whether it's a dog, cat, boat, or bird in the picture. And the purpose of the neural network is it outputs some sort of probability, and we see that the probability should be highest that it's a boat. But again, it's not perfect. It's possible a dog's in there or something like that, but it's very low probability. So boat is most likely probability. So when you read deep learning papers and when you see other people talking about it, that's what these diagrams really mean. It means what's the architecture they're using to analyze their photos. So again, this is a very common type of architecture for deep learning in terms of classifying objects and images, and it works very well. And it works for numbers. It works for recognizing handwritten digits as well. Shown here is the simple neural network, which can achieve like 96 or 97% accuracy. With a deep neural network and the convolution and the deep learning, you can actually increase it to above beyond 99%. And this at this point is better at recognizing handwritten digits than humans. So it works very well. But this marginal improvement for handwritten digits is impressive, but if you consider the fact that you're trying to recognize whether it's a boat or a human in a picture, the disparity is even larger. So deep learning is a very effective technique, and hence its popularity has surged recently. All right, so let's talk about how we're going to apply deep learning to other applications beyond image processing, because there's a lot of people working on image processing with deep learning, and that's where it's getting its glory right now. But let's apply to different verticals. How do we do that? Because it's obviously a technique that works. Well, let's talk about customer churn. Churn, C-H-U-R-N, is the process of a customer leaving your service or becoming inactive in your service, either because they don't want to use the service anymore or they're going to a competitor, etc., etc. If you're running a website where you have active subscribers or active visitors or users, churn is something you need to consider, because once you bring in customers, it costs you a lot to bring in new customers. You want to keep your existing one. And the same case for a telecommunications company. So I want to talk about telecommunications application, because that's what I perform deep learning on. Well, let's look at this target data selection slide. Basically, we're trying to classify our data. Earlier, when I showed you the handwritten digits, it was nice because the data came classified. It came labeled with the ground truth. Like, you knew that handwritten digit of a 0 was a 0 or a 9 was a 9, because the U.S. government's tax citizens' tax money to pay for that manual labor to generate that data. Basically, the U.S. postal workers and high school students created that data set so that we can use to train. But if you're running a business, you don't have time, or you might not have the resources to get such manually generated data. In the case of the image processing, the photo classifying objects in the photos, there's also a very nicely curated, publicly available data set that has been used for training. But let's say you want to apply to a new vertical, like in my case, churn in the telecommunications industry. We don't want to manually classify that. It's too time intensive and inefficient and costly. So how do we generate the target data selection? That's what this is about, this slide at least. First, we're going to show this diagram, and these are customer lifetime lines, LTLs. And there are 3 customers shown here. The first customer has a green symbol on the right, which means that they're active in the service within the 30-day churn assessment window. So if you look at the rightmost window, this is the churn assessment window, and we're going to just use 30 days. Obviously, you can vary that around. We're going to use 30 days in this case. And we see that the first customer is active, has some activity in this 30 days, so we're going to define this customer as still active and not churned. But for the second and third customers, we're going to define them as churned because they don't have any activity in this on the last 30 days. And if we take from this churn assessment window, we go back 14 more days, we're going to define a last call window. In this last call window, we're going to find where their last activity was, or in this case, the last phone call they made. And from there, we can from the last phone call, then we can start to figure out what data we want to grab from these mobile subscribers. Okay, so again, the point of this last call window is because we want to make sure that we grab data on them with ample buffer time In this case, we're defining time before last call 14 windows or 2 weeks, ample buffer time to take action, proactive measures to prevent them from churning, like giving them some promotion or giving them a call to figure out why they might be unhappy with the service to try to keep them in the service. So that's what we're going to do for customers 1 and 2. But the customer 3 there, as you can see, has no activity in the last call window. So this guy, we're going to say that it's too late. They already left a long time ago. It's too late to take any action. But for the first and second one, we're going to define a predictor window, which is the red bar or the red highlight there. And in this predictor window will be a 30-day window. Within this 30-day window, we're going to collect as much data as we can from this customer. Basically, what websites they're looking at, what phone calls they're making, who they're making it to, where they are, their location, their SMS, the text they're making and receiving, time of day. We're going to have all this data. It's huge. It's a huge amount of data, and there are hundreds of millions of customers. And we're going to take that and we're going to analyze whether this person or this customer is going to. We're going to predict whether they're going to churn or not. And if they will churn, we're going to have at least 14 days, again, before the last call to take some proactive measure to keep them in the service. That's the idea here. Okay, so how we're going to use the deep learning algorithms that I've gone over so far to do this? Well, again, the photos and those images are just 2D arrays of pixel intensity data. 2D arrays of numbers. So we can represent customers as an image if we generate a 2D array of numbers, and we can do that according to this slide. Shown here are 4 different customers. The second one is labeled with 1 for churn, so the second customer has churned. We know they'll churn. And so for that 30-day prediction window, we in the horizontal rows is day 1, day 2, day blah 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 all the way to day 30. And then vertically, in the columns, we're going to have whatever behavioral data for each customer it is. For instance, data usage, SMS, voice, websites, location. We can add that all in there, and we can generate an image for each customer. All right, and here's a very similar deep learning architecture from before for the image classification that we found that is successful for predicting if the customer will churn. This so the 30 by 10 input, we're going to make 30 by 10 because it's 30 days, and we're going to use 10 features at least for our example here. And we're going to have the first convolutional layer. We're going to use a feature map of 7 by 1, and we're going to have 4 of these feature maps. So 4 of these feature, and then the second, we're going to have a second convolutional layer where it's a 1 by 10, and we're going to have 2 of those feature maps. So then you can imagine there's 8 mappings by the third layer, this convolution layer 2, by the second layer that is. And then we're going to have a max pooling, a 2 by 1 max pooling, and then we're going to flatten that to a fully connected 1D neural network, and then we're going to have a softmax output of two neuron units because it's either 0 or 1. It's binary classification, and it turns out this works pretty well. Of course, we didn't use the exact architecture for image classification of that boat example because we have to find what works for this one, and that's where a lot of the deep learning effort goes into in terms of the time of the scientist. This is another illustration of that process whereby you have the input of the customer image, and then the different feature maps and convolutions you perform throughout the whole process. And it turns out that this works pretty well. So shown here is a table, a chart that compares the AUC, area under the curve, of the training and testing data for the deep learning architecture. DL-1 is in the second row. In the first row is the SPSS CHIDE model, which is a simple decision tree model. You can first see that it outperforms the simple decision tree model. And simple decision tree model gets up to maybe 0.6, 0.7 between the training and the test at most. But the deep learning model, DL-1, gets between 0.75 and then above 0.7. So it does better. However, you still see that there's a discrepancy between the AUC of the training and AUC of the test. training is higher, which means or which indicates that there's overfitting. Basically, we're overfitting the training, and then once we apply new unseen test data to it, it can't predict it as well. So that's where DL-2 comes in, and there's less discrepancy between the training and the test. So even though the training AUC is lower than DL-1, the test AUC is significantly higher. And there's a reason why the reason why we got that to be better was because we applied routines to reduce overfitting, and that includes something called dropout, which is very similar to bootstrapping idea in the decision tree models. And there's also increasing the input data set also helps. So those are two ways of reducing overfitting. There are other ways like regularization. There's L1, L2 regularization. There's expanding the data set by creating artificial data. If anybody's interested, ask me, I can talk about it some more. There's, what else is there? Okay, so let's go on to, so this shows that we can predict whether or not customers will churn quite well, and it works. It works better than very simple models. And actually we can get better than this, and of course I haven't described what exactly DL-2 is, so you have to read the paper that we published for that. But before we continue on, so now we can predict whether or not customers churn. How can we understand why customers churn? Let's talk about unsupervised learning. So far we have done supervised learning because we have a data set that tells us what the answer should be. That we define whether this customer churn or not. We're going to train the algorithm with this data, and we're supervising the algorithm with this data essentially, and so that it can work on unseen data in the future. However, there's unsupervised learning where we don't have any labeled data at all. Can this neural network just make sense of the data that is provided without any labeling or ground truth? And that's where autoencoders come in. So autoencoders it applies the same concepts as a neural network that we have gone through earlier, but the difference is in an autoencoder, the outputs equal the inputs. So it's essentially performing an identity function. And you can use autoencoders to actually pre-train the supervised deep learning neural networks. But in our case, we're just going to use an autoencoder to perform unsupervised learning. And by that, what I mean is that we're going to get images that maximally activate the hidden units of an autoencoder. And what this does is that for the all hidden units of a autoencoder, it essentially performs something very similar to principal component analysis, PCA, whereby we're trying to see what are the most important components of this data set. And it's more powerful, as I will demonstrate, because we can do it on images. Okay, so let's say we take all the customers and we feed it into the autoencoder algorithm. We find that these are the most prominent components. These 5 images shown here. So the first image is calls and SMS out. So the first 4 columns here are for calls, and SMS out is the last column in these images. And the second one is sort of the data usage that's begin and the end, and there's sort of nothing in the middle. The third image is where you have SMS incoming, so the second to last column here, which is dark. Black is SMS incoming. That's the most prominent feature there. And the fourth image is just data connection in general. It's just uniform throughout the whole thing. And then the fifth image is data connection on sort of like the second 2/3 or second half of the image, which is of course the latter 30 days. Basically, every customer in our data set can be approximately reconstructed with some linear combination of these 5 images. That's basically what this data means, and that's the power of an autoencoder. It breaks down the principal components of your data set. So again, these are all the customers, but we're really concerned about the customers that churn. Remember, we're trying to understand why they churn. So let's perform the autoencoder analysis on customers that churn, only customers that churn. Now this data will have a couple more columns because it's not exactly the same as the data before. But let's take a look at the first images. There are 3 images total that represent customers that churn. The first image is general usage drop-off. So the first few columns here is calls and calls, the calls in, calls out, and then the later columns is data usage. So you can see that in general calls and data usage, there's dropping off in the second half of the 30-day prediction window. And okay, so that might be something expected. Customers that have this prominent feature tend to churn because they're just, for some reasons, slowly or gradually leaving the service, gradually ending their usage. Now, what about the second image? The second image shows strong data usage. And again, this is data only. The voice part is is less important. When they have strong data usage, even though it's increasing in the second half, that still represents a good portion of the customers that churn. And in the third image, it's like pure data. It's very strong data usage, very low voice usage, and very low SMS out. So this brings up raises a question. Why is it that customers that use a lot of data still churn? So again, the basic idea behind this is customers that use a lot of data and really low voice or no voice, they churn. They tend to churn. And this is where human judgment has to come in and figure out what the causation is, because that's really hard. What is the cause of this? But you can imagine that one explanation could be that customers that use a lot of data but not the voice are not socially tied to their phone number, so they don't really have an incentive to keep their phone numbers. So after they're done with the whatever prepaid plans, then they can throw away their SIM and get a new one. So that's one explanation, and there could be other explanations. I'm just providing one. And if that explanation was correct, one way to prevent that would be to give to incentivize these customers to somehow use the voice, somehow to make outgoing phone calls, so that they can get their phone number out there, so that they don't want to lose their phone number. So if we take a look at the customer data set, we can actually see that pick out the shown here in the red outlines, or those are the customers that churn. We can actually pick them out. There are 3 different types of customers, at least shown just from manually picking them out. There's the customers that use a lot of very high data usage and pretty much only data usage. There's 2 where they use the service for a few days, sometime during the 30-day window, and very sparse usage or no usage otherwise. And then almost no usage at all. That's 3. These are customers that tend to churn. So if you're interested in more details, you're welcome to download the paper, all for free, provided by on arXiv. It's published there. And if you have any questions, feel free to email me to ask more.